All right, so very often you're going to be asked these scenario problems with capacitors. We're going to change these things on the capacitors based on how they're the scenarios. And one thing to always look for is there's kind of two major factors when they're doing these changes. You have to either focus on whether they're isolated capacitors. That means Q is constant because the charges cannot be added or subtracted away, or it's connected to a battery, in which case the potential difference is constant. Those are kind of like the two major ones. You could ask other things, but those are like the two major ones that kind of happen. So you need to keep in mind and you need to separate which one is happening. Because if it's isolated, not connected to anything else, right? They'll say isolated or not connected to anything. It means the charge cannot get on or off of it. And if it's connected to a battery, batteries provide, and we'll talk about this more when we get to circuits, batteries provide a set potential difference across them. So then the voltage is constant across them. Okay. I use the word voltage, same as potential difference. So you'll hear that term when we get to circuits. So the potential difference is kept constant there. So let's kind of look at some examples. That's pretty much all there is to it. We just want to look at some examples here. So if an air-filled parallel plate capacitor C naught is connected to a battery and charged to a voltage V naught. So you'll get practice with this later on when we do circuits a bit more in the next unit. So we have this voltage and it's connected to this capacitor here, and it has a capacitance C naught, and each plate acquires a charge Q naught, right? So we're gonna have Q naught here and then negative Q naught here, basically. Suppose the distance between the capacitor plates is halved while the capacitor remains connected to the battery. So here the V is constant. By what factor does the energy stored in the capacitor change? So here, what we're going to think about is we're going to have Q is equal to CV, and we know the V is constant, right? And so if you have the distance between the parallel plate capacitors, let's look at our equation for capacitance. It's going to be epsilon naught A over D. So if I have the distance between the plates, that's the D here, times 1/2, then ultimately you're multiplying the denominator times 1/2 or multiplying the numerator times 2. So you're going to double the capacitance here, and that's going to cause a doubling of the charge. Now, what's our energy? You can either think of it as 1/2 CV squared or 1/2 QV, doesn't matter. Because the C is, we know that this is times 1/2, and now we know the voltage is constant, or we were told because it's connected, that means the energy is going to be times 1/2 over here to keep the equations balanced. So it's going to be by times 1/2. Okay, and then I just did the charge anyway. You could also do it over here with this equation, because now we know the charge is times 2, and we know the voltage is, wait, hang on a second. Sorry, I don't know why I said times 1/2. The capacitance was times 2. Messed up. Times 2 is what I meant. Times 2. But same on this equation, you could say, well, the voltage was constant and the charge went up by a factor of 2. So thus the energy goes up by a factor of 2 as well. Okay. All right. Let's look at another example. We have an air gap parallel plate capacitor, 6 microfarads. Has a space between the plates filled with a slab of glass with a dielectric constant 3. The capacitor is charged by connecting to a 1.5 volt battery as shown. After the capacitor is charged, the voltage source is removed as in 2. So we're going to charge it. We're going to remove it. And we want to know what's the magnitude of the charging here. So we've isolated the capacitor at this point. So Q is going to equal CV. And so the capacitance is going to be kappa epsilon naught A over D. So this is going to be kappa epsilon naught A over D. Or actually, they just told us the capacitance. So it just, yeah. So they already told us the capacitance. The dielectric constant is going to make it. So it's going to be 18 microfarads. And the voltage is 1.5. So that's going to be, 27 microcoulombs. Right, because it's times 10 to the negative 6. And so that will be the magnitude of the charge on the plates there, C times V. And see, we did the dielectric constant 3 times 6 to make it 18 because of that. How much energy is stored? 1/2 CV squared is going to be 1/2 times the capacitance times the voltage. Here, I'm going to have to use a calculator for this. 0.5 times 18 times 1.5 squared is going to be 20.25 microjoules, because it's the times 10 to the negative 6 in there. Now the dielectric slab is carefully removed in 3 without changing the plate separation, nor does any charge leave the capacitor, because we've isolated it, right? So the Q is still 27 microcoulombs. microcoulombs. However, now the capacitance is now 6 microfarads instead. So we need to think about how is the energy is. Now the voltage is not kept constant. So we don't just say like, oh, just replace this with a 6, because we don't know that the voltage stays at 1.5 because it's not connected to the battery anymore. The battery is what was enforcing the 1.5 volts. Now that we've disconnected it, it can float to whatever voltage it needs to be at. It wants to be at. But the Q is kept constant. So which formula do you use here? Well, it's based on what's constant, right? So you could do 1/2 QV or 1/2 CV squared. But again, both are based on the voltage, and we know Q is equal to CV. So you could solve for the voltage, but I just get used to like substituting or replacing it. So I'm going to say the voltage is Q over C. Plug that into here, you get 1/2 Q squared over C. And this is helpful because I know that Q is constant, so that's why I want to use this one. 27 microcoulombs, or I'll just do it at the times 10 to the negative 6 squared. And then the capacitance is now, instead of 18, it's now 6 times 10 to the negative 6 here. So then let's see how much we have here. 0.5 times 27e negative 6 squared divided by 6e negative 6, and I get 60.75 microjoules. So how do they compare? Well, it's 3 times as much. Where did the energy come from? Right? So we should think about it from the energy. Well, it turns out it takes some effort to pull this glass out. It takes work to move this glass out, or it takes negative work. Well, we did positive work. Positive work because we gained energy, right? Remember, work is still the change in energy. So we gain energy, and it took work to pull the glass out. You'll find that the glass is hard to move out, because it wants to be in that plate. And that's because, remember, in the dielectric, right, we're going to have these polarizations. They're going to be attractive in there. And so it's going to take some effort to dislodge that thing. And so that effort, that work, is going to cause an increase in the energy there. Thanks for checking out this video. I hope you found it really helpful. If you'd like more support, maybe you need more multiple choice practice, maybe you just need more guidance and things like that, I have plenty of information on my website. If you look in the description below and go to www.bothellstemcoach.com, I will explain all the ways I help students be successful in their AP classes.